All right. Thanks, everybody. So just a little bit of background here. So I do work at Lexmark. We make laser printers, and so I've been using bitbake professionally for about 6 years now. So we use bitbake to build our laser printer firmware, and I've also been a Rust user personally since even before the 1.0 release, and I've also been fortunate enough to be a professional Rust user for the last couple of years as well. So I want to give a little bit of background for this audience because I don't want to assume that everybody is really familiar with the Rust language and some of its differences and what's interesting about it. So I thought I'd start with a comparison to another language like Go, since that's also supported by the Yocto project. And they're both modern high-level languages. So some of the similarities are that they're both strongly typed languages as opposed to Perl or Python. They also have a very strong emphasis, both of them, on memory safety, very different than, say, C or C++. Another similarity, rather, is that they're also both compiled to machine code, so that gives you some better performance on the nice side, but there's some downsides to that as well. I do want to say just a disclaimer that I know a little bit about Go, but I wouldn't say I'm super experienced, so I do apologize if some of these comparisons are maybe outdated or not entirely accurate, but I think they serve as a good illustration nonetheless. So there are some high-level differences between Rust and Go. One of the big ones is that Go is a garbage collected language and Rust is not. So one of the downsides of having a garbage collector is it doesn't make it great for embedded work, depending on what your definition of embedded is. Certainly, though, if you're talking about operating systems, bare metal code, things like that, a garbage collected language is really going to be problematic. Another difference is that in Go, you still can have null pointers. So there's a lot of memory safety, but null pointer checks are still a thing that you have to worry about. Null pointer references are still a crash that can occur. Rust doesn't have that problem. Anytime you have a reference in Rust, the compiler will guarantee that it's pointing at a valid object. So that is just another class of bug that you can't run into at runtime, which is nice. As a side note, one of the ways that null pointers often get used in languages is for something that's an optional value. And I did want to point out that Rust has a way of expressing that. It's called the option type, but it's a lot safer than null because it requires you to explicitly check, is this present or not? And we'll talk a little bit more about that here in a minute. The other point is that the way that Rust guarantees that references are valid is with a part of the compiler called the borrow checker. So keep that in mind, and we'll come back to that here in a moment. Another thing that's different with Rust, not just with Go, but with a lot of different languages, is kind of its high-level type model. They have something called algebraic data types. So that's a kind of a fancy term, though. So what does that mean in practice? Well, part of that is pretty obvious. Half of algebraic data types is a struct. So you have a type that is a composition of other types. That's pretty straightforward. The other variety, though, is where you have different options to choose from. And a lot of languages kind of have this in the form of enums. But to kind of flesh this out and give a more concrete example, suppose you wanted to have a type that could describe a certain type of fruit. So you've got apple, banana, strawberry, say. And suppose that you had some additional attributes that you wanted to describe about those things. So say if it's for the apple only, you want to be able to describe its diameter. And suppose for the banana only, you want to describe that to be able to tell about its weight. But these things are only used, when the enum is of a certain type. So that's something that comes up a lot when you use enums in other languages, is that you have this problem. For certain cases, you want to be able to do extra information about them. So this is kind of what it would look like if you naively implemented that in the C language. It does have a couple problems, though. So one is that the code has to be very careful not to look at those fields at the wrong time because they might be uninitialized. And the other problem is just that it's not maximally space efficient. So we can fix or at least improve the memory usage by using a union in C. And so we can tell the compiler, we're only going to use one or the other of these at the same time, and that lets the compiler generate better code. And this is sometimes called the tagged union pattern. It does still have the problem, though, that you have to be very careful with your code, right? The compiler is not going to prevent you from looking at the wrong union at the wrong type. So Rust kind of takes this concept, the tagged union concept, and formalizes it into the enum type that's built into the language. So in addition to just having a list of options with an enum, each enum variant can also have associated data. And then the way you get access to that associated data is deconstructing a type through pattern matching. And we'll see an example of that here in a second. But the nice thing about that is it means the compiler won't let you access the associated data that is for the incorrect variant. So going back to our apple, banana, strawberry example, this is kind of how that would look in idiomatic Rust code. So you still have an enum with apple, banana, strawberry. And then for an apple, we're going to have an extra U32 value, which will be the diameter. And similarly for the banana, an additional U32, which will be the weight. For the sake of the example, I'm just using comments here. There's ways that you can name this, but this is clear enough for this example. But you'll notice there is no struct in this case. Everything can be expressed directly in the fruit type. So then if you wanted to get access to some of those associated values, you would use a match statement to match against that value. One thing that's worth pointing out is that unlike C, enum variants are actually namespaced. So you have to say which enum is this particular variant a part of. So this is apple of the fruit type, as opposed to in C, where everything is one global namespace. So if it is, when you're matching against it, you can say if it is an apple, then that means I have an associated diameter. And now only in this branch of the match statement do you have access to that value. Similarly for banana and weight, only in this one match statement, only in the case when it is actually a banana, can you access the weight. And then similarly, if it's the strawberry, then there is no associated data. And so you can't do anything with it because it doesn't exist. It might not be valid. And it's worth pointing out too that this is kind of loosely analogous maybe to Go's type switch. Can be used to similar effect, but also fairly different. One thing that's kind of cool though to point out about this is that this allows the Rust compiler to do layout optimization. So similarly to what a C compiler will do with a union, but not only that, it can actually do this across types. So if you have an enum that contains an enum that contains an enum, or even enum contains a struct contains an enum, the compiler can flatten that out and it can know, okay, this byte and this byte are never used at the same time and generate kind of a maximally efficient representation across all your different types. So that's really cool and kind of an example of, even though Rust is a higher level language than C or some of these other guys, that the compiler can use these high level features to actually generate better code. So just to give another example of the Rust enum, it's very common that you'll see the result type in Rust. And so what the result is, it's an enum that has an OK variant, and it'll have some success type. So in this case, that's a string, or it could have an error variant. And in this case, that could be, say, an integer error code. And so that can be used for the return values of functions that can succeed or fail. And so to use that, you could use a similar match statement as before. And again, only in the success case can you actually access the value that would get returned in a successful case. And similarly, only in the error case do you get an error code. So there's never any confusion about, do I need to check for, is this less than 0? And that means it's an error. They're completely separate namespaces, type spaces that the compiler enforces. And so this is actually so useful that it's in the standard library, except the standard library version has type generics so that you can use any type for your success case and any type for the error case. And so that's very commonly used both in the standard library and across the larger Rust ecosystem as well, all the third-party crates and so on and so forth. So that's neat and handy, but kind of the big promise, at least in my view, of Rust is the promise that there is no undefined behavior in the language. So that means there can be no type confusion. There can be no memory errors like we've talked about, things like buffer overflows, use over after freeze, that are kind of the bane of existence of some other languages due to the security problems they can cause. And even more interestingly, they can use some of these same techniques to fix data races. So the cool thing about this is all these classes of errors are caught at compile time. You don't have to have a test that runs through that particular path, and you don't have to wait until some unwary customer hits that code in production. The compiler will tell you about it and make sure it gets fixed at the very beginning of the development cycle, where it's relatively easier to do that. So I wanted to give some specific examples of kind of each of these aspects and just to start showing some Rust code and get people kind of familiar with the syntax. So as I mentioned, Rust is a strongly typed language. And so that means that if you try to do an unsafe type conversion, the compiler is not going to let you. So for example, if we have a function here that named add, it takes a reference to an integer and it returns an integer. And so all we're going to do is just add 5 to the value of that integer. And like I mentioned previously, this is a reference, but there's no possibility that it can be null because or otherwise invalid. The borrow checker ensures that. So let's say here in our main function, we make a string variable, and then we try to cast that and tell the compiler, well, I want you to treat this as if it were a reference to an integer value, and then pass that to my add function. Well, as you might expect, the compiler does not allow you to do that. So you get a nice error message that says it's not safe to do that conversion, to change from a reference to a string. That's not allowed. So you can use as to say convert from a I32 to a U32 or things like that. But to go between different references of those strongly different types, the compiler is going to make sure that you don't do that. So we talked a little bit about buffer overflows. So the compiler is going to check array lengths both at compile time, if it knows about them, and if it doesn't know the lengths, the sizes at compile time, then it'll do the check at runtime. So here's an example of a runtime check. If we have a function that takes a reference to an array of integers, and it's going to return a single integer, and it's just always going to go and get that second element out of the array. So suppose we create an array that only has a single value and then try to pass that to our function. Well, that would clearly be accessing it after the end of the bounds. That would be a problem. And you'll see here that at compile time, that was okay because the compiler didn't have enough information to know that that was a problem, but it does exit cleanly with an error at runtime. And it's important to point out, though, that this is not a crash. This is not something that was uncontrolled. It's more analogous to, we pulled off the road safely with our hazard lights flashing. The behavior is completely defined, and there's no possibility that you're going to, say, use some value off the stack as a return address. There's no potential for a security problem here. So that's all pretty nice and good, but there's some more insidious errors that you can get, especially in C and C++, like using a value after a free. So to illustrate that, suppose we have a variable named 5, and then we're going to make a pointer that is a reference to that variable 5. The mut keyword you see here, that points out that in Rust, all variables are read-only by default. They're const by default. And so you have to use this mut keyword to say that a variable is mutable, that I want to be able to modify it after I create it. So let's make a new block here, and this could be another function, or it can just be another block in the same function, where we're going to make another local variable, and we're going to change what pointer points at to say that it's now a reference to 6. And then at the end of that block, afterwards, we want to try and print that value. Well, that's going to be a problem because this variable 6 is going to go out of scope at the end of this block. So if this worked, that would mean that pointer was now pointing at freed memory or undefined memory, and referencing it would be an error. And so not only does the compiler flag this and say, hey, this is a problem, but it actually gives really good error messages. And that's something that I have to give Rust a lot of credit for. It's improved a lot over the time I've used it, the quality of the error messages that it gives you. So it says specifically, hey, this variable doesn't live long enough. You start using it here. This is the variable that doesn't live long enough. It goes out of scope here at the end of the block, and then you're trying to use it here. So it gives you really all the pieces of the puzzle that you need to fix that issue. And so this is kind of the first part where we've started to see about borrowing in the language. And so this is, in fact, the borrow checker that is able to figure out the lifetimes of these variables, the lifetimes of the borrows, and ensure that you're never going to have a reference that points at something that for longer than the pointed at object lives. So that's pretty cool. And I think that's an interesting case that the compiler is able to handle. But even cooler still, I think, is iterator invalidation, because this is a problem that I've personally hit many times, and it's often not very obvious to figure out what's going on with it. So here in this example, we've got a mutable array, and it's got 4 values in it. What we're going to do is we're just going to loop over each of the values in that array. We're going to increment each one. And then if the new value is 5, then we're going to try and remove that from the array. And so I think the thing about iterator invalidation that's kind of so sneaky is that it's not always obvious that that's what's going on. It's kind of easy for that to hide in plain sight. Fortunately, though, the compiler sees that and is able to tell us what we're doing. So the problem is that because we're iterating over array, we have a read reference to it at this point. And then when we try to call remove on that function down here, we would be invalidating that existing reference. So it's not valid to have a read reference and a write reference to the same variable at the same time, nor is it valid to have two write references at the same time. So again, this is the borrow checker detecting that this is a problem and pointing it out to us so that we can get it fixed. So cooler still is that the same borrow checker that can find a lot of common bugs in single-threaded code, the language kind of extends this to even find thread problems. So things like data races, the borrow checker can also prevent those things. And kind of the main way that it does that is that in Rust, locks are containers. So in most other languages that I'm aware of, a lock is really just a flag. It just says true or false. This value is being used right now. And of course, there's atomics and things behind it. But you have to maintain manually as a programmer which locks are used for which variables, so on and so forth. So in this example, we're going to make a string, and then we're going to wrap a mutex around that string, or you could say that we're moving the string into the mutex to kind of use C++ move semantics as use their terminology. And so then once we've got that wrapped in a lock, this example is then going to try and access that value directly. And so what you'll see here is the compiler correctly says you're not allowed to access that variable directly. It is now protected by a mutex. So it is kind of using move semantics like C++ does, but what it does, what it gives you the C++ doesn't, is that after you've moved out of a variable, the compiler will prevent you from using that. Whereas in C++, it's just going to be a null pointer or something like that, depending on the semantics. So this actually lets you find and fix that issue at compile time. And again, this is really nice because you know exactly which mutex a particular variable is protected by. There's never any question about which lock you need to grab and so on and so forth. So to kind of complete this out and show what the correct way to go about it would be, is you would actually have to take the mutex. So to do the same thing, make a local variable, wrap it in a mutex. Now you have to call the lock function. That gives you a guard, and then you can then access the value, the contained value, through that guard. And I should point out as well that once guard goes out of scope, that automatically unlocks the mutex. So again, that's another class of bug that you can't run into with Rust of taking a lock and then forgetting to release it. So I do need to step back and say I'm cheating a little bit here, because really everything I've talked about so far has been about a subset of Rust, which is called the safe subset of the language. And that is what you have access to by default. But there are times that you need to do things that are potentially unsafe, or things that the compiler can't verify at compile time, or that the language can't verify at runtime. So that's things like accessing raw references for register values if you're doing a driver or an operating system. And so there's an unsafe keyword in the language that kind of gives you an escape hatch to access those things when you need to. So the nice thing about that is kind of twofold. One is that it means all of your unsafe code tends to be grouped together and very clearly delimited. So if you do have a memory safety issue or some kind of undefined behavior, you know, okay, I need to go look at my unsafe code first and foremost, because that's likely going to be where the issue is. But the other side of that, which is also nice, is that it means all the rest of the time, when you're not using unsafe code, even in your operating system or your device driver, you still have access to the high-level features of the Rust language, so that you can use those really convenient things. Because even in an operating system, most of the code is, policy and data transformation, not unsafe code. So it's really, even in that case, only a very small percentage of your code. So it's been said by many people, not just me, but I have observed that when you write Rust code and you get it to compile, it is going to work correctly the very first time. I've also kind of observed the corollary to that, which is anytime you write unsafe code, it will crash spectacularly the first time. And so that's just a good warning to really try and avoid using unsafe unless you really, really know you have to. Especially for a new user, it can be tempting to just say, "Oh, I'll just put unsafe around this because I think I know what I'm doing, and I don't want to deal with the compiler warnings right now." That will bite you. That is not advisable. So we kind of talked over this at a high level, but what are the summary of the reasons why you would want to use Rust? Well, the big one is the performance. Even compared to another compiled language, it can have really good performance. So one of the nice things that has been added to the language recently is async support, kind of like coroutines. And so there was one benchmark for an HTTP server where the Rust version was able to do 400,000 requests per second, and Go was only able to do 270,000 requests per second. And part of that maybe is due to the lack of garbage collection. But it's nice to point out too that even though it has these really high level languages, really high performance, you can still use those things even on a really low spec system. And so we're using some of these features even on a microcontroller effectively, and I'll talk a little bit more about that here in a minute. So the language designers of Rust put a really big emphasis on what they call zero cost abstractions to keep the overhead of the language low. So that means that even for these really nice features, like say using type generics and things like that, where the compiler doesn't necessarily know all the type information up front, as much as possible, the compiler is going to try and be smart and generate optimized code. So if at all possible, it's not going to jump through a function pointer. It's going to generate a direct call to a specific function. So even though you get the nice high level type generic, you're not having to pay for that with increased runtime. As we've already talked about, it is a much safer language than C or C++ in terms of the memory errors that it can cause. But there's kind of two sides to that coin. So the downside is that it tends to increase the amount of time it takes from I wrote my code and I've got it compiling, because you're going to have to deal with a lot of the issues up front. And especially for somebody who's new to the language, that can be a little frustrating because it feels like you're not making progress. But I think it helps to know that that is normal and that most people go through that. And after a couple of weeks, say, of learning curve, it gets a lot better. The benefit, though, is that even though it maybe took you a little bit longer to when your code even built, I think the time, in my experience, of going from I wrote my code to it actually works and it covers all the edge cases and it doesn't have a bunch of scary security problems, that code is that amount of time is going to be less than a lot of other common languages. Another really nice thing about Rust is that it has a lot of tools that go with it. So there's Cargo, which is the build system and dependency manager. Going along with that is the crates.io, which is kind of the package management ecosystem. It's very commonly used in the Rust world. Almost anything that you need is going to be available from crates.io. It does have an included code formatter, which can really reduce on, bike shedding arguments around, well, should it be 4 spaces or 8 spaces, tabs versus spaces? It helps to have kind of a standard set for that. And then if the Rust compiler itself isn't picky enough for you, if it still doesn't find enough things for you, there is a linter called Clippy, which will find even more things. But a lot of the things that there's a higher probability that things that Clippy finds are not going to be real bugs. So I'm going to point to a real quick demo of Cargo. So it's really only a few commands you need to know. So you can say cargo new to create a new project. And so that's going to create a skeleton. It gives you cargo toml, which is kind of your build metadata, and a source file that's going to do hello world. So to build that, you can just say cargo build, and then you can even run it through that with cargo run. Easy enough. All right. So wanted to give a balanced approach to Rust. I don't want to be overly accused of being a zealot, even though I kind of am. So there are some downsides to Rust. So one of them is that the language is still rapidly evolving. So this means that there are useful features that are in the nightly compilers, but they're not yet stable, and so you can't use them in a release compiler. And there is kind of an allure sometimes to, well, I want to use nightly so I can get all the latest features. But the problem with that is that means you're going to be much more tightly coupled to specific particular compiler versions. for the released versions of the compiler, they've actually done an extremely good job of providing backwards compatibility. We've done many, many upgrades of Rust compilers now, and we've never had an issue with our old code that used to compile, not compiling, or now it has a bug or some weird new behavior. So at least that part of the story is really good. Code size, on the other hand, it is going to be a little bit bigger than a similar program written in C or C++. You might argue that, you know, if the C or C++ program exhaustively handled all the error cases the way that Rust often does, it would be a closer comparison. But, you know, C as written by normal humans compared to Rust as written by normal humans, Rust is going to be a little bit bigger. So that's code size, but on the RAM size, it actually can still be really good. So as I mentioned, we do have a very low spec microcontroller, effectively only 256 kilobytes of RAM, and we are running Rust on there. We are using async features, all the high level features of the language, and that makes that a much more tolerable environment. I think I'm a little bit behind on my time, so I'm going to skip ahead a little bit and talk about, now that I've convinced you that Rust is awesome and you want to use it for all your projects, well, how do you do that if you have a bitbake-based project? So for that, there is a BB layer called Meta Rust. I'm one of the maintainers of that project. And what it gives you is the recipes for building the Rust compiler. It lets you build things like cargo and the tooling around the language. And it also provides kind of the infrastructure to making those things play nicely together. So cargo is really nice for an individual developer because it does want to do everything for you. It's your build system, it's your test system, it's your dependency manager. But the flip side of that is it wants to do everything for you. And some of those things are kind of what bitbake considers its domain, things like downloading dependencies. So there's a little bit of tension there, and we've had to make some compromises to make that work nicely. So this is a project that's used by several large projects. We use it in my work and have for a couple of years in production. And then we're also working towards getting some amount of support into OE core. So let's take a look at cargo-bitbake, which is kind of the main, as a developer, your main entry point to Cargo or Meta Rust. So what that does is if you have a existing cargo program, you can just run cargo-bitbake, and that's going to generate a recipe for you. So as the tool said, there's a lot of things like description and homepage and things that you can set in your cargo toml to affect the generated recipe. But let's just take a look at that. So you can see that a lot of the work is going to be done by the cargo-BB class. So every one of these recipes is going to inherit from that. But it is going to automatically populate your source URI. It's going to look at the remotes that you have configured in your Git repo, figure out where this code comes from, and set that up for you automatically. Similarly, it's going to use your head commit as the source rev. And then one of the main parts, one of the main benefits and reasons why cargo-bitbake exists is that it's able to look at your crate dependencies and tell bitbake about them. So not only the things that you directly depend on, but also your transitive dependencies as well. So we can tell bitbake to use the crate fetcher, which is another thing that that Meta Rust provides, to make sure that these dependencies get downloaded during do fetch, and so that all the normal bitbake mirroring stuff happens, and that during do compile, this makes sure that cargo is not going to try and do network access at that time. The only other thing that's kind of worth pointing out is that we do include a couple inc files from here, and that way if you do need to make customizations, you can do that outside of the generated file, and that leaves you always free to regenerate the recipe using cargo-bitbake whenever you make changes. So a couple more things that I want to point out about cargo-bitbake. It is primarily for generating executables, not so much libraries. You can use it to generate a library, a shared library that you're going to link to from C code, but it's not intended to generate Rust output that then's going to be consumed by other Rust recipes. It is kind of for terminal or the end of your dependency chain. The plus side of that is it means you don't have to generate recipes for all of your intermediate dependencies. But the downside is, especially if you have multiple Rust recipes, that means you're going to be building all your dependencies every time, and you're going to be statically linking them into all of your executables. That's one of the reasons why code size tends to be problematic or not as good with Rust as it is with C and C++. So Meta Rust does support at least having the standard library as a shared object, so that reduces the problem somewhat. But again, any of the dependencies you get from crates.io are going to be recompiled separately. So with that, I just wanted to shout out to the other guys who have helped maintain MetaRust, and thank you to anyone who's contributed to that open source project, and come on in the water is fine. So thanks everyone for your time.